much. So thank you for joining me. Yeah, as Nancy was saying, I don't know how much I overlap with the previous session, so thank you all for those who are still here. Since I'm wearing a mask, that's missing data that I like to fill in with a picture. Okay, so this is me. I'm a lecturer here in statistics and data science, and I work on experimental design and causal inference. The applications of my research are pretty wide-ranging, environmental policy, education, health, other areas as well. Okay, so what is causal inference? This is when we want to go beyond determining associations between variables and actually say, I want to estimate the causal effect of a particular intervention on a particular outcome. Okay, and what does it involve? It means that we are going to design and analyze either an experiment or an observational study. Okay, so that's how I'm going to define causal inference. Other people might have different definitions. And I'm going to introduce causal inference through the idea of the potential outcomes framework. There's a variety of different ways about thinking about causality in a structured way. The potential outcomes framework is one popular sort of model for thinking. Another one is called directed acyclic graphs, where you draw a bunch of arrows between variables and try to figure out like the causal graph. I'm not going to talk about that today. It's an equally interesting framework, but just a different way of thinking about causality. So let's say one day I have a headache, I'm sad, so I take some medication. I take some paracetamol. I wait, and an hour later, my headache's gone. So I go off and I do some yoga. Okay? So the question is, did the medication cause my headache to go away, based on the information that you have right now? And I would argue that this is currently an ill-defined causal question, because I haven't said what would happen if I didn't take the medication. Okay? So in causal inference, we always ask, compared to what? What is the effect of taking medication compared to not taking medication? Okay, because you could also ask, what's the difference between taking paracetamol versus ibuprofen, right? There's a bunch of different questions we can ask, and I would argue it's not a causal question unless we're comparing two different scenarios. So we can think about this as two parallel worlds. One where I took some paracetamol, my headache went away and I did some yoga. The other, I did nothing and my headache remained. So we call these two different potential outcomes. There's the potential outcome if I took the active treatment here, and there's the potential outcome if I took the control treatment here. So this is the idea of counterfactual thinking about sort of parallel worlds. Then the causal effect is the difference in my headache status between if I took the paracetamol and I didn't. So the causal effect is the difference between two potential outcomes. So here in this case, I would say, yes, the paracetamol worked, because I'm comparing it compared to not taking anything, my headache went away, and it would not have gone away otherwise. Oops, sorry. So I'm going to put some maths on this. There's not a lot of maths in this talk, just a little bit. We have our treatment, our intervention. I'm going to call it W. It's a binary variable. W equals 1 if I take the active treatment. Here, this is taking paracetamol. W equals 0 if I do nothing. And then I'm going to define these potential outcomes, Y. And what's a little bit unique about causal inference is that we have it be this function of W. Okay, so this is a little bit different notation than sort of other areas of statistics. So I have Y when W equals 1, and I have Y when W equals 0. And when W equals 1, my headache goes away. No headache is 0. And here I still have a headache. So I've just written down for this example, I'm only using binary variables. It's very easy to extend causal inference to continuous outcomes. It is much harder to extend it to continuous treatments, right? It's very easy to think about two parallel worlds. It's very hard to think about an infinite number of parallel worlds. Okay, so now I can actually estimate a causal effect with maths, right? I can get a number. So here my causal effect is -1, 0 for no headache, -1 for headache. Now let's consider a different situation where if I hadn't taken the medication, I still get better. I still go to yoga. Okay, and this really speaks to the power of the potential outcomes framework, because now in this situation, what is the causal effect? It's 0. But if I hadn't thought about the counterfactual, I wouldn't have realized that the causal effect here was 0. I just would have said, I woke up, I had a headache, I took my medication and went away, right? So this is a really simple idea, but I would argue very powerful, because usually when we do statistics, we think about the data that we observed, and now we're thinking about data that we never could observe, okay? And so even just this framework really makes you think very structurally about causal inference. Now, the problem here that I've been ignoring so far is that I can't see parallel worlds, right? I only have one world. I either took the medication or I didn't. So the fundamental problem of causal inference is that we only ever observe one potential outcome, okay? Fundamentally, it's a missing data problem. So how do we solve this missing data problem? There's a variety of ways. The simplest is that instead of thinking about just one person at a time, I'm going to extend to many units, okay? So instead of thinking about an individual level treatment effect, I'm going to think about the average treatment effect across, say, n people. And the advantage of this is that I can't observe my counterfactual, but at least I will have observed for some people what happened in both scenarios, right? So I'll have some people, let's say I have 9 people, I can think about what happens if they all take paracetamol. I can see what happens if none of them take paracetamol. So these are the same 9 people, just to be clear. And I can see that there is going to be a positive average treatment effect here. Fewer people have a headache when they took it versus they didn't. And if I can make some assumption about these groups being comparable, right, then I don't need to necessarily know for each person what would have happened in their opposite situation. I just want to know on average for the population the difference between taking paracetamol and not. So it's a much easier problem than just looking at an individual person. Okay. I'm also happy to take questions throughout, by the way, so feel free to interrupt me. So how do we actually estimate the average treatment effect? Well, there's 2 different main types of causal studies. We have randomized experiments and observational studies. And I'm sure you've all heard about them before, but the question is what fundamentally is different about them from a causal inference perspective. And I would say whether treatment assignment is controlled by the researcher or not. So in both cases, I consider treatment assignment random, but in a randomized experiment, I know the process of randomization. I was the one who said, you get treatment, you get control, right? Versus an observational study, that's out of my control. I still consider it random, but maybe the person decided what their treatment was. Or maybe the treatment was rainfall, and so the earth decided what treatment was, okay? The consequence of this is that in a randomized experiment, my treatment groups tend to be very similar to each other because my randomization is independent of any characteristics of the people. So I should have similar age range in both groups and similar gender balance, for example. Versus an observational study, no guarantees, right? So I might have one group that's exclusively seniors and one group that's exclusively teenagers, and that's not very good for me, right? So the consequence of this, in randomized experiments, causal inference is pretty straightforward. I do want to clarify that doesn't mean it's easy. It depends on the experiment. You know, we can still do nice fancy statistics, but pretty much always I can get a causal answer. In observational studies, it's difficult, and I think very important to recognize sometimes impossible, right? When we're doing statistics, one of the most responsible things we can do is say, I can't do anything here, right? Say, I'm sorry, I can't get a causal estimate for this situation. But that doesn't mean it's not always impossible. There are ways to still achieve causal estimates in observational studies. I'll talk about that more later. So why is causal inference easy in randomized experiments? Well, we can show, and I won't, but you can, that the estimate of the treatment effect is unbiased. And this is a consequence of the fact that each group is comparable on their covariance. So the only difference between the 2 groups is which treatment they received. On the other hand, observational studies, it's hard because we can have confounding. This is a word that people use a lot and sometimes have different definitions, okay? So I'm going to put up mine. That doesn't mean you'll agree. But I'm going to say confounding is when I have background characteristics like your income, your age, your race that affect both which treatment you receive and your potential outcomes. Okay, so when that happens, then causal inference is hard, and then effect estimates are biased unless I do careful statistical adjustments. Okay, so I'm sure we've all seen really bad examples in the world of people using association to apply causation, but since I'm giving a talk on causal inference, I have to include one. Okay, so here is a study that looked at the association between arts engagement, so basically people going to museums or the opera or things like that, and mortality. Okay, and this study, I just want to clarify, the original study was quite responsible. It just reported that these things were associated with each other. It did not use any causal language. This is how it ended up in the media. Okay, so go to the museum once a month and you'll live 10 years longer, no gym required. Great, fantastic. So why is this a problem? Okay, well, let's consider something like going to the opera, okay? Perhaps there's some confounding variable there, which is that, I don't know about you, but for the people that I know that regularly go to the opera, that's basically no one that I know, but they're probably, a lot of them are filthy rich. Not all of them, but some of them, okay? And then filthy rich people also probably tend to live a little bit longer. So what happens is that there's an association between these two variables, right? But there's no actual causal effect. Okay, so I'm sure you've all seen examples of this. This is just one of my favorites. Okay, so how do we fix confounding? We fix it through achieving covariate balance. Right, so as I mentioned in randomized experiments, this is something that we are guaranteed to have on average at least. Versus observational studies, we don't have covariate balance by default. And if we did have balance, this is going to mitigate the influence of confounding. So in this example, right, if your people who went to the opera happen to have exactly the same income as people who didn't go to the opera, then I might believe you if you say, okay, people who go to the opera live longer if the two groups are exactly comparable on income. So even though the confounding exists, by balancing, I've mitigated the confounding. Okay, so how do we do that? I call this the design phase of observational studies. And our goal of designing an observational study is I want to take a bunch of observational data and I want to try to approximate a randomized experiment as closely as possible by achieving covariate balance. And I will talk about one method for doing that later. But first, I do want to just talk about randomized experiments a little bit, because I hear two misconceptions commonly about randomized experiments. So the first one I hear is that randomized experiments aren't really relevant because they're only used in clinical trials, and unless you're doing clinical trials, no one really needs to learn that. That's like old-fashioned statistics. Okay? The other misconception I hear is that once you have a randomized experiment, statistics is super easy. You don't even need a statistician anymore, because it's just like, as I've just said, causal inference is straightforward, so why do you need me? Okay, so let me try to remove some of these misconceptions. Okay, so some examples of modern randomized experiments in the last few years. A/B testing is a huge field. This is basically what they call randomized experiments in the tech world. You have a button that says buy. I want to know whether the button should be blue or green, A or B. You run a big test on all your users, and you see which one gives you a better outcome. It's a randomized experiment with a different name, okay? So I have a friend who works at Meta, or at least she did, I don't know about after the layoffs today, that she works on Threads. She's trying to get people to sign up for Threads. If you haven't heard of it, it's like the new Twitter competitor from Meta. And she runs hundreds of A/B tests all the time where she says, okay, what if the number of characters in the preview is 100 versus 110? Does that make a difference? So just constant A/B testing. Education. Experiments in education are very trendy in some countries and less trendy in others, whether you actually run randomized experiments. One fun one from about 10 years ago, there was this trend that people thought that if you have kids read to a dog, it helps them improve their reading skills. This experiment did find that. I think it's sort of mixed results. But yeah, it's kind of fun. People actually did a randomized experiment to see whether this worked. Social policy. This is an example from Australia. So they looked at people on JobSeeker, and they wanted to know whether they moved some people from face-to-face consultations to online consultations, whether it made a difference, basically. Right? So if you're on JobSeeker, you have to go to employment services. And they wanted to know whether the long-term outcomes were different. The answer is a little bit complicated. It was better on some things and worse than others, not like maybe a huge difference. Crime. People did a randomized experiment where they improved street lighting in certain streets, and others they left alone, active treatment, control treatment, and then they looked at the crime rate in those two areas. So these are just some examples of how randomized experiments are probably being used in areas that you didn't even realize. Okay, second misconception. They're simple and I don't need statisticians. Okay, it depends on the experiment, right? Maybe you're right if your experiment's pretty simple, but there are a lot of complex experimental designs out there. Factorial experiments is one of them. So this is when I have more than one treatment, and I want to evaluate not only each treatment, but how they interact with each other. So I might think that the sum of two treatments is greater than the individual parts, for example. This is very common in industrial experiments like manufacturing. So I found this study that was looking at tungsten alloys. These are some materials used in aerospace. Apparently it's really hard to cut. And in their factory, they tried a bunch of different combinations of voltage and pulse frequencies to see what was the most efficient way to cut the alloy. Okay? Not too complicated, but still I would like you to talk to a statistician first. Fractional factorials, this is where we get extra complicated. So I have a factorial experiment that I want to run, but I have so many factors that I don't even have enough units to do all of them. So you can imagine when I have just like 2 factors, you don't have that many combinations, okay? But let's say I have 10 factors, and each of the factors has multiple different levels. So in this example, they were looking at 10 different microplastics, and I think each microplastic they wanted to vary it from like 0 to some like 5 different levels of microplastics. And they were looking at whether it was how toxic they were on aquatic organisms. But they didn't have enough organisms to test like 2 to the 10 different combinations. So then you have to very carefully design your experiment to be able to estimate the things that you care about, but you won't be able to estimate everything. Okay? So the design informs which interactions, for example, you are able to estimate. Okay, so hopefully I have removed some of your misconceptions, if you had any, about randomized experiments. Now moving on to observational studies. I have a little bit less on this because I'm pretty sure all of you are believe observational studies still exist and are used. I don't really have to sell that to you. But here's one case study just of how good data and good statistics can make a really big difference. Okay. So one question is, if I have higher intake of dietary cholesterol, does this cause higher levels of blood cholesterol and thus cardiovascular disease? Okay, so previous consensus, say 20 years ago, was yes, you eat more dietary cholesterol, it results in more cholesterol in your blood, this is bad, okay? Currently, we say actually no. So the current consensus is that dietary cholesterol does not influence blood cholesterol, but saturated fat does influence blood cholesterol. The problem with this is that cholesterol and saturated fat consumption are very highly correlated. So for example, something that's high in cholesterol is eggs. You often eat eggs with sausage and bacon. Those have a lot of saturated fat. So they're almost, if you look at graphs, it's they're almost perfectly correlated. And so that's why we thought cholesterol consumption was bad, because it was impossible to disentangle these two things. But then better data collection and better statistical methods resulted in better controlling for confounding the saturated fat consumption. And when you do that, you see that there's actually no association between dietary cholesterol and cardiovascular risk. Okay, so this is something where, good statistics actually changed, medical knowledge. In general, how do we use causal methods in observational studies? How do I approximate a randomized experiment? Well, obviously that's the whole field of causal inference, tons of methods. Natural experiments is just one that I want to highlight because it tends to have kind of fun examples. So a natural experiment is where I didn't control randomization, but somehow something happened randomly. For example, if I want to know the effect of income, very hard for me to randomize, impossible, right? But if you win the lottery, suddenly you go from one income to a much higher one, and it's random. So people have done lots of studies about what the effect of winning the lottery is on various outcomes of your life. Another natural experiment that's kind of famous was one where they looked at the time that your case was up in front of a judge. So were you up in the late morning or the early afternoon, before or after lunch, which presumably is random. And they found that people who were right before lunch had much worse outcomes, like much worse sentences, probably because the judges were hungry. Okay, so it's called the Hangry Judge Study. It's a bit disputed, so some people are saying it's actually not random when the cases were assigned. So unclear, but fun example, right? Matching I'm going to talk about next. All these other ones I'm not going to talk about, and there's many more. It really just depends on what data structure you have available and what assumptions you believe versus don't. So all these different strategies, it depends on how many treated versus control units you have, whether you believe you have all the observed confounders, things like that. Okay, so I'm going to just talk about matching as an example. So matching is one way we can achieve covariate balance. Matching works really well when I have a small pool of treated units and I have some big potential pool of control units, and I'm going to try to construct something that looks like a randomized experiment from this pool. Okay, so what I do is I take each treated unit, these are my W equals 1s. So I take this person and I go to my control donor pool and I try to find someone as similar as possible to them, but the only difference is they happen to not get the treatment. Okay, so I look for another orange woman. And then I do the same for each of my treated units until I have now I have my final pool, where if I look at that selected group, it looks very much like a randomized experiment. I have the same number of green and orange people in the treated and control. I have the same number of men and women. It actually can even be better in some cases on balance than a randomized experiment. So what is the interpretation here? If we produce high quality matches, I can say that I've approximated a randomized experiment. And basically within each pair, it's a coin flip whether you happen to have received the treatment or happen to have received the control. The problem with matching and many, many causal inference methods is that it only controls for observed confounding variables. Right? It doesn't fix anything that I haven't observed. But if I believe that I have collected all of the variables that I need that affected both your treatment and your potential outcomes, then matching is a really great strategy. But if there's some confounder out there that I didn't observe, I can't do causal inference. And you have to be responsible and just say, sorry, can't do it in this case. So I'll give you a little case study to wrap up with. This is a project I worked on that was evaluating carbon offsets. It's a work in progress. And there's this specific type of carbon offset that the Australian government pays for called human-induced regeneration, HIR projects. And basically what happens is the Australian government pays landowners to stop grazing cattle with the goal that trees grow. Okay, so we're trying to grow trees. The treatment is you get paid to not graze cattle. Okay, and this is a really, really big program. It's the 5th largest nature-based offset in the world by carbon credit issuances. Here's a map of all the different projects over Australia. So big land area we're talking about. Just to give you a little preview. So the question, right, is we're trying to grow forest, okay? Does this look like places where it's easy to grow forest? No. Okay, so you can already guess that maybe the program might not work so well, but the Australian government says it's great. Okay, so let's think about some hypothetical scenarios. Okay, I look at a project area, I look at forests over time, and let's say the project started here and I see forest growth over time. I might be tempted to say, great, it's working. But this is exactly the I took paracetamol and my headache went away situation. I'm not thinking about the counterfactual. We have a little bit more information here than we do in other settings because we have forest cover before the project started. Okay, so let's say I had information before the project started. Now I'm already a little bit wary about whether this did anything, right? Because clearly forest cover was already increasing. Yeah, I'm not convinced it did anything. Now if I saw this, okay, maybe the project did something, right? It was increasing before, but now it's increasing faster. So a little bit more plausible. But then let's say I find a control, do some matching, right? I find a control area, and I see this. Is it working? No, right? Okay, so this is exactly what we did. We took like little cells of areas within the project. We matched them to places close by outside of the project area that are similar on rainfall, soil, things like that. And then we said, okay, we're going to model the forest cover over time. If we see something like this, we know it's not working. If we see something like this, then it is working, okay? So what did we find? Okay, so the solid line is the control group. The dotted line is the treated group. Is it working? No, at least in my opinion, this is not working. And the Australian government is spending millions of dollars on it. So that's a very sad note to end on. Just if you're curious what is happening in like the frontiers of causal inference right now, a bunch of like famous people in causal inference wrote a paper last year. Sorry, this is my please look away from your screen reminder. On some of the challenges that are currently facing causal inference. I won't go through all of them, but I'll just highlight a couple. Interference. So this is, usually we assume independence between units. This is very common in lots of statistics, right? But what if my outcome impacts you, right? Let's say it's vaccines. Whether I get the flu impacts you. Anything with social networks, anything with spatial data. This is a challenge for causal inference, as it is for a bunch of statistics. Heterogeneous effects. So if I don't think that there's just one single treatment effect, but I think it works differently in different groups, how do I handle that? Sensitivity analysis. So this is, let's say I have an unobserved confounder. How would that affect my result? Would it completely get rid of my result or not? LLMs, everyone's talking about that. Benchmarks. So in machine learning, we often have these publicly available data sets where you can test your model to see whether it works well or not, right? You categorize dogs versus cats or handwriting or things like that. In causal inference, because we don't actually know the true answer most of the time, it's hard to compare methods. Everyone's doing it in different ways. So is there a way that we can think about a more universal approach to evaluating methods, for example? And that's all I have. I'm always happy to chat about causal inference. So please talk to me. I also am always looking for collaborative projects in environmental policy and climate change, regardless of whether it's causal inference or not. If you're interested in the carbon offsets project, my colleagues built that website. I didn't, but it's beautiful. And then here's the slides and my website. So thank you. Yeah, I have a question. Yeah, so I think it can be great, but there's a trade-off in terms of you often are increasing precision in exchange for worse variance. So inverse propensity weighting, for example, so what the goal there is to produce groups that are have comparable covariate distributions with by using weighting. And if it works, it's really great. But sometimes you end up with a situation where some people have weights that are like 1,000 and other people have weights that are like 0.2. And so you can end up with very variable estimates. So yeah, it's a trade-off, right? Sometimes if your experiment really isn't very well balanced, I would consider it. But if I had a reasonable degree of balance, I might not. It might not be worth the trade-off. It really depends. But it is a really interesting area, like how much should you do covariate adjustment? Should you throw in a regression model, like once you've done your experiment with covariates to try to get a more precise answer? Again, you can have, there's trade-offs with you can increase your variance at the, at the cost of, you reduce your variance, but you can increase bias. There's always trade-offs. Yeah, good question though. I didn't know that the FDA was actually like officially recommending that. There's also like a very not trendy thing, which I think should be trendier, which is before you do your experiment, there's something called re-randomization, where you don't want to, you kind of constrain, you say, I want a randomization within a certain like sphere, essentially, and you re-randomize until you get something where the balance is good enough. The problem with this, again, is if you can kind of extrapolate this to thinking about, okay, well, why don't I just create an experiment with perfect balance? Then it's not random anymore. So you kind of have, like, there's another trade-off there as well. Yeah.
I have a question on that. Is inverse probability weighting on the study designed to do inverse probability weighting? Does you end up with a reduced power? And if you did plan for it, how do you compute power assuming you're going to do inverse probability weighting in a randomized controlled trial?
Yeah. I would worry about reduction in power for sure. Yeah.
I mean, if I was doing it, I would want to do sensitivity.
Yeah.
Just curious what other people think about this.
Yeah.
How do you incorporate, like, is there an explicit way that you incorporate directionality into the mathematics? So, I mean, this sounds stupid, but that's my intention to do yoga in the future for men. But like, so I think very much in like a weather front or something that, it's like time is causal, space is not. A lot of time I was thinking about. Does the mathematics change, or you posit a direction?
We usually like to assume that away.
Yeah.
Yeah.
Like having high blood cholesterol doesn't, maybe that's causal by, like, obviously, like we're assuming directions here, but is there a mathematical way to also infer directionality?
Yes, I'm a little skeptical of it. So that's called causal discovery, where you have a bunch of variables and you try to figure out the direction of the arrows between them.
Yeah.
I don't know much about it.
Okay.
So I don't want to speak to whether it is, how good it is, but it is a thing people do.
Okay.
Sorry, that made it sound more negative. I really honestly don't know anything about it. Yeah.
In your experience, do you have a preference when you're doing causal inference to do the matching, or would you want to take in more samples from the control group and do like IPW or multiple regression or something, or in general, do you think you get those better sort of estimates from your matching?
I tend to like matching just because it's very easy to explain to other people, like who aren't, causal statisticians. It's just, you're like, look, I produced matches, and it's just like very nice. That doesn't mean it has the best statistical properties. I agree, probably weighting is often better, but it does have you accidentally blow up the variance sometimes problem. It's also, there's different norms in different fields. So some fields love weighting and hate matching, and I respect that sometimes it is better to just kind of go within the norm of the field because they often end up basically the same. So I would say matching only works when you have a really big control pool. And my students love to make the mistake of you have an equal number of treated control units and then they try to match and you end up with exactly the same result. It only works when you have like a big potential pool versus weighting works when you have more comparable sizes. So it's a little bit more flexible in that way. Yeah.
Yeah, another question on matching as well, actually. Have you ever come to the situation, had this before, where there's multiple identically good matches, and how you handle that?
Yeah, just pick one randomly. Okay, or you can do many-to-one matching.
Yeah.
So you can have, say, 3 control per 1 treated. Again, there's trade-offs in terms of variance and bias and all those things. But yeah, often if you do a sensitivity analysis with different matches, like you get the same answer. So I don't usually worry that much unless there's something like your data is really small or something like that. Yeah.
Clinical trials, they're talking about the synthetic arms, so that you can use the existing trial data from past and compare it with current trial that is ongoing or maybe future or so. So how credible that is in your opinion when you're doing this mashup?
Oh, okay. So you're saying that I use data from an old trial as like a comparison group.
Yes.
Okay, I'm not familiar with that. I guess it makes sense, but there is some risk that you have different data collected, you had different protocols. There's a lot of things that can go wrong in experiments that aren't just which treatment you got. So I would be wary, but like if you have good data and information about it, that sounds like a possible thing. I do think it's great to use previous data to inform the design of your next experiment. I think that's really like valuable, or using an observational study to inform the design of an experiment. But using it as an actual like treatment comparison, I'm a little bit more skeptical of. Yeah.
Going to randomized experiments, you mentioned fractional factorial experiments. How advanced is that field? And if we wanted to learn more, where do we go?
Yeah, it's pretty advanced. They've been around for a long time, but it is still an active area of research, I would say. Most experimental design textbooks will have like a short chapter on it, I would say. I'm happy to, talk offline if you want.
Thank you so much.
Thank you.